So today I will talk more about how one actually uses the code song. And in order to do this, of course, we first have to install the code. And you can go ahead and try this now so that later, before the exercises, I can come and check if there are some problems. So when you clone the code, it's important that you put this minus minus recursive here. Otherwise, you will not have the correct version of class installed and it will not work. Apart from that, it should be as straightforward as installing class. So you just go to the folder, you make song, and after that you can run the code with two files. And both of these files are very important because they are also a documentation for the code. So if you want to, in class, you have this explanatory.ini file, which also exists in Song, but in Song it's a bit, it's not very well maintained, it's a bit messy. So in Song instead we have the documentation files which are ini intrinsic.ini, which explains most of the parameters, and pre-quicksongrun.pre, which explains most of the precision parameters. So if you want to learn how this works, you should look into this and this file here. And then when you run it, because this is a very quick run, it should really finish relatively quickly and give you some information. And if you just go and try to execute this, if it works, you are all set up for the exercise session later. Otherwise, I will have to come and check if I can help with the problems. All right. Then, if you want to learn something about the second-order perturbation theory and the way it is implemented in Song, this is the best reference, which is the PhD thesis of Guido Pettinari, which is very detailed, has lots of information, and has the equations that are implemented in the code as written in the conventions of the code. So this is the kind of reference, but more for the physics, not for how to use the code. Okay, so then if you have installed Song, you will have a folder which has all of these subfolders, and I will quickly tell you where you can find what. So the most important one is the source folder. This is exactly the same way, so it's organized exactly the same way as it's done in class. And in the source folder, you have the different modules. So you have perturbations2.c, transfer2.c, and here is where all of the physics is. So if you want to change anything in the code, this is where you will be spending most of your time. Then you have the main folder. This is, again, exactly the same way as it's done in class. This contains the song.c file, and the song.c file, just like in class, the main.c, just calls all of the modules. The song.c does not only call the song modules, it also calls class modules. So this is the most significant difference. So it goes through, calls all of the class modules, and after it's done with calling the class modules, it will just start calling the song modules, and after that it will free all the memory it has allocated. Okay, then there is the include, which includes the header files. Then there are pre and ini folders, where there are some predefined precision and initialization files. And this is, of course, very useful. So, for example, in the pre folder, there are files which have a set percentage of accuracy for some maximum multiple range. So if you don't want to spend too much time on tuning the precision parameters, you can just use some of these presets. But in reality, when you compute something that has not been computed before, you will spend a lot of time tuning the precision files. Then there is the class.git folder. And in this class.git folder, there is the class version that is used by the song code. So all in this folder is a complete installation of class. It will have its own subfolders. It has its own source subfolder, own main subfolder. And there are all the class modules defined within this folder here. The version class.git is a fully functional version of class. So you can also just go to class.git and make linear runs. But of course, I would not recommend doing this because this one is the modified version of class that is used for Song, and it does not have all of the features included that the more modern versions of class have. So you can use it, but if you do linear computations, really, you should just use the newest and most modern version of class that's available. But this is completely functional, and you can use it. Then there is a Python folder, which has the Python wrapper for Song. And this works also just like the Python wrapper for class. But I'm not going to talk a lot about the Python wrapper for Song for the simple reason that when you use class or you use Song, the codes are based on the same structures, but the usage of the code is very different, because in song, each run that has a usable precision, each run takes a couple of hours. So while in class you can go to the Python wrapper and you make a few hundred runs of class and then you visualize the results in a very nice way from the Python wrapper, that's fast. In song that would take a very long time. And this means that there is rarely a need to call song through the Python wrapper. You can just call song through the terminal, store the files, and then load the files in a Python wrapper. The overhead for doing that is very small. But if you want to use a Python wrapper, there exists a Python wrapper for song that is functional. Then we have the output folder, where the code will write the output. And the build folder, which has all the compiled objects, the tools folder, has all of the math-related functions that are not specific to the physics. So this contains only things that are not related to the physics. This includes all of the physics, and the rest is not really very important, so I'm going to skip over this. All right. Then let me talk a bit about the structure of song and how the code is actually executed. So these are all of the modules that are contained in song that are not already contained in class. So it starts with the input2.c. And the input2.c works exactly like the input.c of class, with the only difference that the input2.c reads the song and the class parameters. So when you call the code song, you just specify one ini and one prefile, which contains both class precision parameters and class input parameters and song input and precision parameters. And the code input2.c will just read both of them. Then there's a perturbations2.c module. And the perturbations2.c module is one of the most important modules, of course. It is the one that will evolve the second order system from the time where you set your initial conditions to the final time, essentially. And this means in perturbations2.c there are all of the physical equations. The second order differential system is coded into this file. There are the quadratic sources that are built from the perturbations that class stores. So if you want to modify some of the evolution equations, you would go here. And when you look at the code, there's always a distinction between the quadratic terms and the pure terms. This is how we call them in the code. And the pure terms are the perturbations that are second order perturbations that couple to other second order perturbations. And the quadratic terms describe how two linear perturbations couple to a second order perturbation. And then typically the differential system is built by first collecting all of the pure terms, then collecting all of the quadratic terms, and then just adding them together into the differential system. So if you want to modify and you have some new equations, then you have to look, does it affect the pure, the quadratic, or both? And then find the code in here and modify it. Then the perturbations2.c also writes some files for the line of sight sources. This is very similar to the way how class works. Only that, of course, there are many more line of sight sources that are written here. And that's perturbations2.c. Then you have a Bessel2.c, and the Bessel2.c will just go through and compute some geometric coefficients for the line of sight integration. After that, you go to transfer2.c, and transfer2.c is just a module that will take the line of sight sources at second order that were filled here, take these to compute the present day perturbations using the second order line of sight integration. And then we have the bispectra2.c, which is actually a new class module. I talked about this a bit yesterday, which will compute linear primordial bispectra. And you give it as an input, you request some specific primordial shapes, and then it will compute a bispectra corresponding to these primordial shapes. And then you have bispectra2.c, which takes the output of the transfer2.c and computes the intrinsic bispectrum from the transfer functions. And then finally, which I did not talk about yesterday, there's also a module called spectra2.c. And spectra2.c is like a spectra.c, just takes the output of the transfer2.c and computes power spectra. But here you have to be very careful, because the code only computes second-order perturbations. So what Spectra 2.c will compute is a second-order perturbation combined with another second-order perturbation to give you a second-order power spectrum. But there is the equivalent sized, or a term of equivalent importance, which would be a third-order perturbation combined with a first-order perturbation. And of course, we do not have access to this term. So the Spectra 2.c output is not a complete result. It is only a complete result if, for some reason, the first-order perturbation is 0. So, for example, when you compute B-mode polarization and you have cosmology where there are no tensor contributions to linear order, that means you have no B-mode polarization at linear order, then the B-mode power spectrum at second order is a 2 term plus a 1-3 term, but the 1-3 term is exactly 0. And in this case, what Spectra 2.c computes is actually the full result. But you can only really use it if the the corresponding first order perturbation is 0. So the code has options where you can output like the temperature, second order temperature power spectrum, but that is not a meaningful quantity. So this one you should only use with B modes or magnetic fields. And then finally, there is the Fisher.c module for a class that we have added, which will take all of the bispectral information and compute the Fisher matrix from there. And what I want to highlight here is that the structure, how this is written, really follows very closely the structure of class. The conventions are largely the same. Each of these modules has an init function, which will initialize the module, which will do all of the computations and fill the different structures. Each of these has a free function, which will then free all of the memory. And then there are also internal and external functions that can be called for these modules. So the structure is exactly the same as in class. Then the naming conventions is that whenever we talk about something that is second order, we just add a 2 to the name. So you see here, for example, perturbations 2.c is the module, and then internally in class, the perturbations module is called with PT. And then when you look through the song code and you see something that is called PT2, you know this is the perturbations 2 module. So this is very simple. As soon as you see something with a 2, you can think, okay, in class it is this, so this is the second order version of that module. Okay, then what is important, when you want to call song, you will call it with the ini file and the precision file. And in class, this is the same, but in class, it's of course perfectly fine to put whatever you want into the initialization and the precision file, and the code does not care about this. And this is the same in song. You can put whatever you want in these files. But I think it is more important to separate these in song than it is in class, because the runs just take very long. And it is often such that you need to really tune the precision parameter, because you have a limited time that you have available to do your computations. And so you will typically modify this precision file a lot until you find converged settings that do not take too much time, while you will typically not change your initialization file. So I would advocate for really not putting whatever you want into these files, but being systematic about it and using the initialization file to tell the code what should be computed, and the precision file to tell the code how accurate it should be computed, and not mix these two. And this is also how we have given the presets. So in the precision folder, you find different precision files, and then you can use the initialization file to tell the code what you want to compute, and then you can use just different pre-made precision files to see if that works, or work on these yourself. Okay, then these files, the initialization and precision file, they contain both song and class input parameters. And some of them are actually shared between both codes. So for example, the cosmological parameters. You don't need to specify cosmological parameters once for class and once for song. Of course, both of them will use the same cosmological parameters, so you just put them once. And then there are some files which will only be read by class. So for example, class precision parameters, how many points in K you want to sample. And then there are some parameters which will only be read by song, which would be the second order sampling precision parameters. And some of these, actually, song will overwrite some of the class parameters. And this is for the simple reason that if you tell if you tell class to compute on a k-grid, on a specific k-grid, and then you tell song, you specify your second order three-dimensional k-grid for song. Now song knows at which values of k it needs to evaluate the first order transfer functions. And then it is just very natural to simply tell the class code to compute the perturbations at exactly these k values that will later be needed for the song code. So if you put some class parameters and they don't seem to make any change, it's just because the song parameters have overwritten them. But these are just very few, typically the ones related to the k sampling. The rest of the class parameters should not be overwritten. And as a general guideline, because class is much, much faster than song, you should really use good precision parameters for class, because if you wait hours anyway to get the result of song, there is no point. You can really take a few minutes to compute the class results. There's no problem. So as a general guideline, you should choose class parameters that are relatively good, and then your precision, the real precision settings are done by the song parameters. You don't want to be in a case where your precision is limited by the class parameters. Okay, then if you do not put any parameters in, this works also the same as it is in class. You will have some presets, and the parameters will be put to some standard values. And while this works extremely well in class, it is not so simple in song, because in song there is much bigger trade-off between the computation time and the precision. So it is not really clear, these presets, should they be such that the code runs relatively fast? Should it be such that the code runs accurate? And then, depending on which output you want, what accurate means is actually different. So for some of the outputs, you need a lot of the small k modes. For some of the outputs, you need a very fine time sampling. So it's not really as simple to find good templates that are just universally good to use as a standard value. So we did our best to get some useful default values in there, but typically you should think about the problem that you're trying to solve and find parameters that are working, and not rely on these presets too much. Okay, this is the basic structure of the input files and the precision files. Now I'm quickly going to show you how this will look like in practice. Here, this one is how you can specify your cosmology. And if you look at this, you will notice that this looks exactly as it does in class. So you really just can take a class input file and use this for the specification of the cosmology. Then now for the song-specific parameters, you have the output setting, and the output setting really tells the code what kind of output you want to have. And here are some of the most important options that you can put. The first one would be bispectra. This is temperature bispectrum, E mode bispectrum. You can also put B mode bispectrum, but that is incredibly small. So these are the typical inputs that you will give the code. Then here you call the CLs, temperature CL, E mode CL, B mode CL. You can also put. This one here is when you want to compute the cold dark matter bispectrum. This one when you want to compute the cold dark matter power spectrum. These one here are, for example, for magnetic field power spectrum. And then typically you want to compute the Fisher matrix if you're interested in the non-Gaussianity. And if you want to compute the Fisher matrix, you also need to tell the code which bispectrum types you want in the Fisher matrix. And the intrinsic is the one that is for the second order part of the calculation. So the intrinsic bispectrum type refers to these two quantities here. So if you just select T-bisp, then intrinsic is T-bisp. If you select T-bisp and E-bisp, then intrinsic is the combination of T-bisp and E-bisp. And then you have the option to add some of the primordial shapes. For example, local non-Gaussianity, equilateral non-Gaussianity, and there are some other predefined shapes, or you can put your own shapes in here as well. And then finally, there is the option to specify which kind of modes you want to compute in the code. And the 0 here is just scalar modes. So this is what you typically do in class if you don't have a tensor to scalar ratio. Then you can put 1 for vector modes, 2 for tensor modes. And in class, because there are no sources for higher modes, so you only have scalar, vector, and tensor, there is no option to go beyond 2. But in song, due to the quadratic sources, there's no limit at all. You can put whatever you want here. So you can put 3, 4 higher higher dimension tensors, there's no cutoff. But in practice, what we find quite luckily is that the scalar modes still dominate the result, at least for temperature and E-mode polarization. Of course, if you want B-mode polarization, you have to put the 1 and 2, and then 3 is small again. So typically, if you put 0, 1, and 2, you should have most of the important terms. And if you want to look just at temperature and polarization, only putting 0 should already be very good. But in principle, you can put whatever you want here. And then also, this works the same way as it does in class. You can set your output parameters. In class, you have the, for example, perturbations verbose that you set to 1. Now you just have also quantity perturbations 2 verbose that you can set to 2 or 1 or whatever you want to specify how much shell output you want to have while the code runs. So then this is the very complicated part, which is selecting the sources that you want to have in your second order system. And here I wrote that you should be careful, because if you don't understand this, you shouldn't change it. This is the standard preset, what you see here, and this is what you should typically use. So first, we have on the top, we have the settings for perturbations 2.c. And perturbations 2.c is where you solve the second order Einstein-Boltzmann equation. And we have quadratic sources, quadratic Liouville, and these two terms will just tell you if you want to have the quadratic sources in the collision term and if you want to have the gravitational quadratic sources. And by default, you just say, yes, I want them all. And then you can also select specific sources. So you can say, for example, I want to have time delay in my Liouville terms, yes or no. I want to have redshift terms, yes or no. I want to have lensing, yes or no. While the name lensing and redshift and time delay here, of course, in the differential system do not really make too much sense. It's just the way how we have labeled them. And then you can individually activate or deactivate some of the sources. And then we have the second part here, which refers to the line of sight sources. So these settings here, they affect what happens in transfer 2.c. And again, you have the option to activate scattering. And here you have, for example, the pure, which is the second order part, and the quadratic, which is a combination of first order perturbations. You can turn scattering sources on or off. This one I will come to back in a second. And then you can turn the geometric terms on and off. For example, you can turn time delay on or off. You can turn redshift on or off, lensing on or off. And here you see that in the presets, all of these are turned off by default. And this is what I explained yesterday, because we want to, for example, take lensing not by solving the second order system, but by making an expansion in weak angles, so weak deflection angle expansion. So this means we have to set it here for no, otherwise it will be double counted. And in fact, the only term that we include of these here is the Sachs-Wolf effect, the integrated Sachs-Wolf effect, but we take only the early part of the integrated Sachs-Wolf effect and not the contribution from dark energy. Because the contribution from dark energy, again, is a late time effect, which is complicated to compute. So we have the second order version of integrated Sachs-Wolf effect only for the matter radiation transition and not for the second part of the transition. And then here, coming back to this delta tilde in line of sight, yes, this is exactly the part that will absorb the redshift terms that are set to no here. So if this one is set to yes, this one definitely needs to be set to no. Otherwise, you will compute things double. The code should complain if you put both of them to yes. So in a nutshell, if you understand what you're doing, you can modify this. You can select individual contributions and see what kind of impact they have on the second order evolution. But if you don't understand this, you should just leave it at the presets. Otherwise, you will get uncontrolled, not properly converged results that don't make any physical sense. Okay, then coming to the precision parameters. And the precision parameters are very important because in class you can say, okay, if I want to have a very, very well converged result, I'm just going to take 10 seconds and let the code compute. And in Song, typically you don't have the option to have perfectly well converged results. You have to make some trade-offs. And here we have done for we have done a detailed convergence analysis where we take the most important numerical parameters and we fix them to some values and then varied only one of the parameters to see at which point we reach convergence. And I'm quickly, so what we compare here is signal to noise, because of course we want to plot it as one single number that is a good measure of how accurate the code is, and then signal to noise just takes all of the complete calculation of the code and condenses it into one number. And then if we are well converged for signal to noise, of course we hope that this means that we are well converged for all of the quantities that are needed along the way to compute this number. So then here we have the different parameters. And here this n tau is a number of time steps, and is a number of time steps for the line of sight integration. And this is because in perturbations 2.c, the code automatically sets the number of time steps because the evolver is adaptive, and the evolver decides how many time steps we need. So there's no parameter related to perturbations 2.c. But then perturbations 2.c also has to store quantities that are later used for the line of sight integration, the line of sight sources, and this n tau is the number of times that we sample the line of sight sources that will then later be integrated and transferred 2.c. And what we see here is that if we take, it's very few, only 10 points, we are quite far off, then it quickly converges. And if we take something like 100 points in the time sampling, we are relatively well converged. Of course, this one here, if you look at the dots very carefully, you see this is kind of a percent difference between this and this point maybe. So it's not completely perfectly converged, but if we are kind of aiming for percent level convergence, and then you can use about 100 points here, and it should be fine. This one here is the K-grid, and the number of points here is not the number of points that we sample, it's the number of points in one dimension. So the actual points that we have is roughly this number cubed. And then again, you see if you take 50, you're pretty far off, and then you come down here and you need about 150 or 160 probably to get a good convergence. And of course, this parameter is very expensive to increase. This parameter here is actually not that expensive to increase, but this is quite expensive to increase. Here you have a number of multiples that we have in our second order hierarchy at perturbations 2.c. And in class, in fact, you get relatively good accuracy if you take only few number of multiples. So if you take 30 in class, it's actually not too bad. But for song, what we see here is that, in fact, you need to go to about 80 or 90 or maybe 100 multiples in your hierarchy to get a good convergence. And the difference to class is coming from the simple fact that in class, it's always one multiple coupled to the next neighboring multiples, coupled to the next higher multiple, and so on. But in a song, we have the quadratic sources. And the quadratic sources can immediately source higher multiples. So this means that, in fact, we reach higher multiples faster than we do in class. Or there are more options to generate larger multiples by these quadratic sources. And then we find that you need about 100. And this parameter is also not the cheapest. It doesn't mean you have to you have to solve more differential equations, but it means that your differential equations, of course, become significantly larger. And then if you combine this with the cut in M, if you take a scalar vector tensor, in principle, if you take 80 multiples, you could go by M from 0 to 80 to take really all of the modes that exist. And then it will become extremely expensive to do this. But I don't have this on this plot. We have checked, which is actually very fortunate, that the magnetic moments don't really give much of a contribution, and you don't have to go to 80 in M if you go to 80 in L. Otherwise, it would be a complete disaster. This parameter here is a step size, which means it becomes better in this direction, and is not super important. It is related to the bispectrum integration, and it does not directly represent a physical parameter because this is a mathematical expansion of the delta function in the bispectrum integration into spherical Bessel functions, and then you introduce a new integration over this parameter R. And of course, one has to choose this small enough such that this integration converges well, and we see that there's no real problem. I mean, to get delta of 20 or 10 or 5 is no problem. It's just to show that this extra step that we have introduced is well converged. And then here we have the maximum k that is required. And one sees that one needs to go to 0.25 or something like this to get a good convergence. And this parameter is also very expensive because, of course, if you go to a higher k max, you have to use a higher nk as well. Because if you increase your k max, but you don't increase nk, you lose sampling. So what we've done here is, this is not just a plot of k max, it is a plot of k max keeping the density of points fixed. So this means every point we go up here, we will also increase nk consistently. And finally, this one here is the number of sources Lmax, now not in perturbations 2.c, but in the line of sight integration. And for class, this Lmax will always be 2, and there is no ambiguity about it. But in song, we see that we need to put Lmax to something like 10 to really capture all of the effect, which means that we have 11 line of sight sources that contribute to the integration. And these are essentially the most important precision parameters that you need to tune. And then you can see what you kind of should take, and then the code will take a relatively long time to run if you put all of the parameters here such that they are well converged. Good, then now how does one put these parameters actually in the precision file? So we have marked all of the parameters that are related to song with the underscore song. And then you first specify the K1 and K2 sampling. And this is done relatively similar to the sampling in class. First, you specify your K-min in relation to tau 0. You specify your K-max in relation to tau 0 over Lmax. This is simply because if your Lmax is larger, of course you need to have more, your K-max also needs to be larger to make sense. So you always want to keep the K-max in relation to Lmax fixed. Here, this is giving you now the minimum K1, and this is giving you the maximum K1. And in Song, we have decided to make it such that K1 and K2 are always sampled completely equally. So the minimum for K1 is also a minimum for K2. And for K3, there is the geometric structure means that we cannot simply sample K3 on the same grid, but I'll talk about this in a second. And then we have here parameters for the sub-Hubble evolution, K-step sub. And this is just a linear grid in K for the sub-Hubble scales, here with an example step size of 0.1 in K. And then on the super-Hubble scales, we have a linear and a logarithmic step size. And the logarithmic step size 1.8 just means that each next step is 1.8 times the step before. So if you decrease this, it becomes more precise. And this defines a logarithmic sampling on the super Hubble scales. And this one here defines a linear sampling on the super Hubble scales. And the code will just check whatever is smaller and use this, which means that initially you will have a logarithmic sampling, and then eventually you will go to this linear sampling, and then eventually you will go to this linear sampling here on the sub-Hubble scales. And then there is one extra option that you have, which is K-max for PK. And this again defines a new logarithmic sampling if you want to. So the normal K-max is defined here in relation to Lmax for CMB perturbations. But if you want to compute some large-scale structure perturbations, you don't really need to have this fine linear sampling. You're quite happy with the logarithmic sampling. And for this reason, you can define this K-max for PK, and then it will go to the maximum K for CMB quantities, and then from there start a logarithmic sampling up to this K-max here. And this then gives you a grid for K1 and a grid for K2. And now we still need a grid for K3. And for K1 and K2 and K3, we know that they have to lie on a delta function, so they have to close to a triangle. Which means if I have already specified K1 and K2, there's a certain range of scales in which K3 can fall, which is just K1 minus K2 to K1 plus K2. And in this range of scales, we can try to use the same grid that we have for K1 and K2. So we just take the grid K1, K2, and then we look the range for K3, and then we fill it with the points that we have also taken for K1 and K2. This works very well, but there's one problem. And this problem is if K1 is very large and K2 is very small. And it's related to the fact that we have a logarithmic and linear samplings combined. So if K1 is very large, then it is typically in a linear regime which has big step sizes. And K2 very small, so it's in a logarithmically finely sampled step size. And then we compute which is the range for K3, and we see, well, it's essentially K1 minus a very small region to K1 plus a very small correction. So it is a small range centered around K1, but K1 is a large, so it is in the linear region, which means that when we look at this and we want to use the same grid for K1 and K2, then K3 will be exactly at the same point as K1, and there's only one point in this sampling region. And using only this one point is in fact very bad, because it is also not a random geometry, but it's a very specific geometry where K1 and K3 are exactly the same size and K2 is very small. And when you look at the structure in the K1, K2, in the angle between K1 and K2, you typically see that there is a certain shape in the angle between them. And this shape is not really dependent if K2 becomes very small. This shape is kind of preserved. So you really should look at the angle between K1 and K2. So how do we solve this problem here? There's different ways how this can be solved. If you look into the ini file, I haven't put it here on the slide, there are different strategies for K3 sampling. One of the strategies is angle, where you will just take a number of points and sample the angle between K1 and K2. But this typical one that one uses is the predefined. You just have to set a minimum number of points. And then the code will try to put the same grid for K1, K2, and K3. And if it realizes that in the K3 grid for one configuration, K1, K2, there are less than 5 points, then it will just add some extra points until it has 5 points. And in this way, we always have a certain minimum sampling guaranteed, while for the cases where K2 is not very small, we have the typical sampling that we also have for K1 and K2. And this works very well. So of course, 5 is not very much, so you could increase this to 15 or 20 to get better results. Okay, then we're using these parameters here, you have your K-grid set up. Now you have to think about your time grids. And for the time grid, we have 2 very important parameters. There are options to set your completely customized time sampling with lots of different parameters, but typically you don't need to do this. Typically you are interested in these 2 parameters. The first one sets a time sampling for the quadratic sources. And this is in perturbations 2.c. The evolver will decide itself on the steps. But the quadratic sources need to be interpolated or at the time steps that the evolver selects. And in order to interpolate them, we compute them in class on a given grid in time. And then here we set how fine this grid in time should be that class stores for song. And typically this one here just increases the memory usage a bit. It doesn't make the code slower, so there's no reason to put a bad sampling in here. Then the second time sampling is the one for the line of sight integration. And this is the much more critical one. And here it's just that you have computed the line of sight sources, and now you store the line of sight sources and later try to use them in the line of sight integration. And there we take here in this example file a step size of 0.4, which of course is much worse than 0.03 here. But it's because this one takes a lot more time to compute, because this setting here only affects what class does and how class writes out some of the quadratic sources, nothing else. This one here is really a song precision parameter that is important for the second order evolution, so this will affect a big part of the computation. And this one is also responsible for this n tau here, because making a plot for this is very, very boring. Okay, then we have time sampling and K sampling, so what we need now are the multiples. For the multipoles, the most important parameter is which maximum multipole are you interested in. And this is 100, of course, very, very low. And this is in the quick song run.pre, simply the reason why quick song run.pre is so fast, because you only compute up to L equal to 100. It doesn't really do very much. Then you have to specify a cut for the second order Boltzmann hierarchy in perturbations 2.c. And here we have selected all of them to be 12. This is for photons, ultra-relativistic species, and polarization. And this simply defines how many differential systems you solve. And at the maximum cut, the Boltzmann hierarchy is closed by a closure relation. Then in the second order, you don't only have your second order equations, you have the quadratic sources. And here all of them are set to -1. And -1 simply means that you use the same cut as for the second order system. So if you already put 12 equations for your photons, then you might as well put 12 quadratic sources into these equations. But if for some reason you want to not give all of the equations that you solve their quadratic sources, you can put less here. But typically, also for time computation reasons, this is not very expensive to put them to the same number as these ones. If you increase these, it becomes more expensive, but if you increase these, it doesn't really become that much more expensive. So typically, you want to set them to -1. But maybe you're interested in finding out what specifically the quadrupole source does, and then you can use this to cut off the higher multiples automatically. And this, again, are the setups for the hierarchies in perturbations 2.c. And then we need to set the hierarchies in transfer 2.c. And here, this tells the code to take 5 line-of-sight sources for temperature, 5 line-of-sight sources for polarization. And again, we can put the quadratic ones to 5 and 5. We can put them also to less. We can also put them to -1, which will make it automatically takes the same as here. Again, there is no reason to put these to anything that is worse than these. But the code has the flexibility to do that if you want to do this. Okay, so these are the multiple cuts that you can use. And then if you have done that, you can run the code with your ini and your prefile, and the final output of the code will be this Fisher matrix output. And the Fisher matrix simply tells you the following. Here you have the different shapes that you have selected. So in this case, local, equilateral, and intrinsic. And then here again, you have local, equilateral, intrinsic. And the Fisher matrix now tells you if you, so the diagonal elements of the Fisher matrix, when you take the square root of them, you get the signal to noise. So this tells you if you observe the bispectrum and you look for a specific shape in the bispectrum, and then you compare that shape or the bispectrum in that shape to the noise that you have for this specific shape, how is the ratio between the signal and the noise in that shape? So here, when you take the square roots of these numbers, you get the signal to noise. And the off-diagonal ones are related to the correlation between the different templates. So there is, in essence, you take one shape and the second shape, and then you scan the correlation of these shapes over the noise. And from here, you can construct something that is a bit easier to understand conceptually, which is a correlation matrix. The correlation matrix simply tells you how correlated different shapes are. So you can look, for example, at the local. Of course, diagonally, all of the correlations are 1, which simply means that each template is perfectly correlated with itself. And then you can, for example, see here that the local and equilateral shape are anti-correlated about 9%. Which means that they are not completely orthogonal to each other, but have some overlap. And then this one here, the intrinsic, gives you the second order bispectrum that was computed by Song. And what you can already see from this line here is how it correlates with some of the known templates. So for example, you see that it is 73% anti-correlated with local template, which means that the second order computed bispectrum looks a lot like a local bispectrum. But it is also 14% anti-correlated with the equilateral bispectrum, which means that it does not look perfectly like a local bispectrum, but it has some bigger contribution to the equilateral configurations. And of course, you can use different primordial shapes here and then see how the intrinsic bispectrum is correlated to all kind of primordial shapes that you're interested in. And then finally, the probably most interesting one is this FNL matrix here, where on the diagonal we have 1 over the square root of the Fisher matrix, diagonal part. So this tells you just how much the signal is suppressed by the noise. So for example, you see that the local template, if you go to L max equal to 100, this is important. If you have access to smaller scales, of course, the signal to noise will become much better. If you only can observe up to L max equal to 100, then this local template that you have given the code is 50 times below the noise. So you have no hope of seeing anything in the data. Of course, for the local and equilateral templates, this number is not meaningful because they are predefined and you could redefine them to make them simply larger, keeping the same shape. But for the shape that we have defined as local with an unspecified amplitude, this one is now turns out to be 50 times below the noise. And for the equilateral shape, even about 170 or 146 times below the noise. But again, these numbers are just convention by whatever you define to be your primordial templates. Then the intrinsic one, of course, this amplitude here is not just convention because the intrinsic one is computed by the code and the amplitude is fixed. This is not just a shape, but it is actually the full contribution that was computed by the second order code. And if you can measure up to 100, then this is 37 times below the noise. So this number already tells you some actual physics information. And then on the off-diagonal parts of this matrix, we have the ratio of these off-diagonal Fisher terms to each other. And this has a very specific interpretation. So for example, let's go to the lowest row here, which is the intrinsic row. The intrinsic row, this means if I have a bispectrum in which there is an intrinsic bispectrum imprinted in it. So let's say I have an intrinsic bispectrum, but now what I measure is I look at my data and I search for a local bispectrum. This is this row here. So intrinsic cross local is exactly, I have an intrinsic bispectrum, but I'm searching in my experiment for a local bispectrum. What will I measure? And this term now tells you that if you have an intrinsic bispectrum, but you look for a local bispectrum, because the two shapes are correlated, you will find a local bispectrum of amplitude minus 0.53. And then this one tells you how much the intrinsic bispectrum will contaminate your local FNL measurement. And in this case, we can see why it is. I mean, we can understand why it is minus 0.53. First, the templates have a similar amplitude. This one is in fact a bit larger in amplitude. So of course we expect this to be it's hard to say, but roughly to be of order 1. And then we look at the correlation and we see these shapes are anti-correlated with some coefficient of 0.73. And then we can say, okay, well, this looks reasonable. If we have an intrinsic bispectrum, we will mistake it for some amplitude of a negative local template. And the same also, of course, works for the equilateral one. Here, the number is significantly smaller just because the shapes are not as correlated. So if you have an intrinsic bispectrum, you measure an equilateral bispectrum, you will get less of a bias between the two because the correlation is smaller. But you can also look at other things here. You can, for example, say, let's say I have an equilateral bispectrum and I measure a local bispectrum, how much will I get a contamination here? Or you can also, for example, say, let's suppose I have a local bispectrum, but for some reason I measure with the intrinsic template. And then you would get this contamination to your intrinsic template. But of course, no one would do that. So the important part of this matrix is really the lowest row, which tells you first, if you search for the intrinsic bispectrum, how much is it suppressed by the noise? And you want this to be smaller than 1 ideally. And then if I look for other templates, how much will they be biased by the presence of the intrinsic bispectrum? And this is kind of how you read the output of the song code in this Fisher matrix here. Okay, so this is essentially what I wanted to say. Then I will